Welcome to this lecture in the ongoing series of lectures on real analysis. Today we'll be looking at a very interesting theorem called the intermediate value theorem. Despite it being very intuitive, it is also very powerful. These are the problems for today. I won't be recalling anything from last time because this is a new module. Now let us immediately get into the statement and the proof of the theorem. So what does the intermediate value theorem say? It's something which is very intuitive. So what we have is a function defined on a closed interval which is continuous. The function is assumed to be continuous, and with this property, what does this property say? It just says that fa and fb have opposite signs. So if fa is positive, then fb is negative, and if fa is negative, then fb is positive. So that's what this is saying. So what the conclusion is that there is some real number strictly between a and b, such that f vanishes on that real number pictorially, which is really the heart of the, or rather the motivation for even coming up with a theorem like that is the following. So we have, let's say this is a and this is b, and let's say the function is negative on a. This is the value of the function on a, and let's say this is the value of the function on b. So since the function is continuous, you can't lift your pen, and at some point you need to cross the x-axis, which is the point where the value, which is at least a point where the function will take the value 0, and that's it. So the function is the theorem is very, very intuitive, but we need to prove it. The proof is not so obvious despite the simplicity of the statement. So okay, here is the proof. Here is our proof. There are multiple very nice proofs of it. So, assume fa is less than 0. The other case would be that fa is greater than 0, but that is completely analogous, so I won't do it. So assume fa is greater than 0, then fb must be greater than 0 by hypothesis. And now here is the key definition. Let S be those elements in a comma b such that f is strictly less than 0 at each point of this interval. So this is our definition. One should stare at this definition for some time and figure out what this is trying to say. Basically, suppose x is in S, then suppose this point is in S, then what it is saying is that on this entirety of this interval, the value, the sign of the function remains negative. Basically, does not cross the x-axis anywhere here. That is what this definition is. And clearly, a is in S. That's trivially in S because fa is less than 0. However, by the continuity of the function at a, since the function is continuous everywhere, it is also continuous at a, there is a neighborhood around a where the function remains negative. And if you want to see that formally, I won't write the details, but let's say this were equal to -1 just for concreteness. This is a -1. Then if you take epsilon equals half, what we know is that there is a delta for which all the points in this delta neighborhood, meaning all the points between a and a plus delta, they are mapped less than half distance away from this point. So all of these points will be in this tube, and hence they will all be negative. So what we observe is that by continuity of f at a, we see that S has elements strictly greater than A. This is a key observation. Immediately by continuity. Again, let me say one more time. Fa is negative, so there must be a region around A where Fa remains negative. That is what continuity tells us. Okay. And now let x naught equal supremum of S. And there are some multiple cases. So case 1, f of x naught equals 0. Then we are done, because we were trying to locate some point strictly between a and b where the function vanishes. Now x naught cannot be equal to b, because at b the function takes positive value. So this would simply not happen if x naught equal to b. So x naught is less than b in this case. X naught is also strictly exceeding a, simply because S has elements greater than A, and therefore the supremum of S also will be greater than A. So x naught, assuming this case, in fact not even assuming that case, just by this writing we see that x naught is strictly greater than A, and in this case we see that x naught better be less than b, and therefore x naught satisfies the requirement for C. Alright, great. So this case is favorable. Case 2 is that this is less than 0. Okay, if that were the case, then there is some point x naught here. Let's say this is x naught. And here also the function is negative, and the function is negative through and through. The function is negative throughout this region. So this would be the graph of the function, something like this. But by the same reasoning as we applied to A, the continuity of f at this point would say that actually there is this whole neighborhood around the point x naught such that the function remains negative on this entire neighborhood by the continuity of f, because it takes some negative value on x naught, and by continuity there is a neighborhood such that it remains negative throughout this neighborhood, which means that x naught is not really the supremum of S, because the function is negative throughout here, and the function is actually negative on a larger region. So x naught cannot be the supremum of S. There is something larger than x naught present in S. So this contradicts the definition of x naught. So this simply cannot happen. Case 3 is that fx naught is greater than 0. Okay, so we need to rule this out. Alright. So here we have x naught, and let's say f takes this value, some positive value here. And since x naught is in it cannot take positive value, because so it perhaps could take positive value, but let me argue that it cannot, because x naught is in the supremum, x naught is equal to the supremum of S, and if you take anything less than x naught, then that point is in S. Anything less than x naught is in S. Please convince yourself. And therefore, if you take any point less than x naught, on this entirety of this interval, f takes only negative values. It does not take 0 or positive values. So if you just take anything less than x naught on this entirety of the thing, the function is negative. So the function is negative, 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 but suddenly it has become positive, and that will contradict continuity. How? This is the way. So on x naught it is assumed to be positive. Therefore there is a neighborhood around x naught where it remains positive. Again by continuity. Right? But as we just argued, that as soon as you take a point smaller than x naught, there the function value is negative. So that's a contradiction. So this contradicts, this is a contradiction. Contradiction to what is hard to write, but you can write it. So the first case is favorable, where we are able to locate what we wanted to locate. This is a contradiction and this is a contradiction. So that's it. I kind of muddled a little bit in this case, but I hope it is clear. So this is one of the proofs where I did not write all the gory details, but by now we have enough maturity to follow intuitive arguments. This is a rigorous argument, it's just that some of the steps I haven't written in detail. So fine, the conclusion is that at some point the function needs to hit the x-axis, and that's where it vanishes. Great, this is also called the intermediate value theorem, but let me state another version of it. Let me also write that this is a form of the intermediate value theorem. Now let me discuss another form of the intermediate value theorem. So it says the following. Suppose I is an interval. It could be half open, half closed, both open, infinite, semi-infinite, whatever kind of interval. And you have some continuous function. Then we want to say that the image of that interval is also an interval, perhaps of a different kind. So if you start with an interval like this, let's say like this, then maybe you will get a finite image. That's possible. This is an infinite interval, but maybe you'll get a finite image, right? So when I say infinite interval, I mean infinite length interval. So again, this is also very intuitive. If you try to counter it via some examples, you'll see why this is true. But before we prove this, we will prove some other lemma. We'll prove this lemma that let J be a subset of R such that whenever we choose 2 points, we choose 2 points in J with A less than B, then this closed interval in its entirety is contained in J. So J has this special property. This is called convexity. Then J is an interval. And again, this is not at all hard. This should be an exercise, but let me prove it. So let P equals infimum of J and Q equals supremum of J. And assume that both are real numbers. So it is possible that P is negative infinite or Q is positive infinite and stuff like that, but I will just argue for the case when both P and Q are reals and leave the other cases as exercise. Assume both of them are reals. Now if P and Q are in J themselves, then it is clear that J must be equal to this closed interval, because J is clearly contained here. P is infimum and Q is supremum, so no point in J is less than P and no point in J is greater than Q. So this containment is clear, but now by this property the reverse containment is also clear. So if both P and Q are in J, then we are in good shape. So now suppose P in J but Q is not in J, then we claim that J equals, or rather, okay, let me not claim anything. So then J is contained in this guy. Again, it's the same reasoning. Nothing in J can exceed Q and nothing in J can be less than P. And by assumption that Q is not in J, we see that actually nothing in J can also be equal to Q. So everything in J should be contained here. So that's the similar thing. However, but P comma Q minus epsilon, this is contained in J for each epsilon. Right? So because if that were not the case, meaning if there was an epsilon such that this whole thing was not contained in J, then what would happen? So suppose there is epsilon such that, let's say this is P is in J, and this is Q, and this is Q minus epsilon, and suppose that this guy is not contained in J, then what does that mean? That means there is at least one point here which is not there in J, right? But it cannot be the case that no point here is in J. If none of the things here are in J, then supremum of J cannot be equal to Q. So for supremum of J to be equal to Q, there must be points here which are in J, and as soon as there is one point here which is in J, all of these points are in J by this hypothesis, and therefore this interval in particular is also in J. So we crucially need this hypothesis here. Anyway, so we conclude that for each epsilon greater than 0, this closed interval is contained in J, and therefore we have the reverse containment, because as soon as you pick a point here, we see that whatever that point is, P comma that point is contained in J. That's what this says. So therefore this containment happens, and hence P comma Q equals J. And similarly you can do the other cases. So you can do the case where P is not in J but Q is in J, and the case where P is not in J and Q is not in J. All of them are very, very similar. So let me leave those cases as exercises. Okay, so much for this lemma, and now we can prove our above thing. So now we can give a proof of this. So proof of what? Proof of this. So we show that J, which is defined as f of I, has the convexity property What does that mean? That means this property, that whenever a comma b are in J, then this whole closed interval is in J. So this is what we'll argue, but that is very simple, because suppose we have 2 points. This is some a and b, and let's say a is less than b. So these are in the image. Okay, what should I name them? Let's say this is C and D. Okay, and I is some interval, something like this, some interval. So on C it takes the value A, and on D it takes the value B, the function, and we want to show that it will take all the values in between. Well, this is precisely this guy, which has been stated somewhat differently, but I mean, that's the conclusion. So if you achieve the value A and achieve the value B, then you achieve all the values in between, and therefore this closed interval is contained in J. How do you show that? What you can do is, instead of working with this function, you can work with the following function. You can work with G defined as f minus a plus b by 2. So if you consider this function, then G is of course continuous. It's a difference of two continuous functions. F is continuous, and this constant function is of course continuous. So G is continuous, and G of C is what? It's minus. It is A minus b by 2, which is negative because A is less than b, and G of D is A plus b by 2, I think. Yeah, it should be that geometrically, but let me check. If I substitute b, then this is b minus a by 2. Sorry about that. And that's what it should be. Okay, so this is negative because A is less than B, and this is positive because A is less than B again, and therefore this must take the value 0 somewhere, which means what? If G takes the value 0 somewhere in between, then G takes that means that F takes the value A plus B by 2 somewhere in between. So that means this value is definitely achieved by the function F, and you can do this for anything in the intermediate. So if you take this point in the intermediate, you just shift your function by that quantity, whatever is that quantity. Instead of A plus B by 2, you put that number and repeat this argument. So F achieves all the intermediate values. If F achieves A and F achieves B, then it achieves all the intermediate values, and therefore J indeed has the convexity property. And by the previous lemma, J must be an interval. Okay. Again, nothing is complicated here. Only this proof was a little bit non-trivial, but everything else is fairly obvious and natural. So this is what one can call the intermediate value theorem. Whichever you prefer, you can call this the intermediate value theorem if you want, or you can call this fact the intermediate value theorem, where you say that if F achieves two values, then F also achieves all the values in between. Of course, you have the hypothesis of continuity, otherwise this is simply not true. So yeah, so that's all that I wanted to do in this lecture. As usual, like, comment, share, subscribe. Also have Patreon, the link is in the description below. Thank you for listening, and I'll see you next time.